The universe is a vast and wondrous place. It is filled with billions of galaxies, and each galaxy contains billions of stars. We live on a small rocky planet orbiting one of those stars. From our tiny vantage point, we look out into the cosmos and we wonder, what is out there? How did it all begin? And what are the rules that govern everything we see? These are the questions that have driven humanity for centuries. They push us to build bigger telescopes and more powerful instruments. We are explorers, not of land or sea, but of space and time itself. Among all the strange and beautiful objects in the cosmos, one stands out as the ultimate mystery. It is a place where the laws of nature as we know them seem to break down completely. We call it a black hole. To understand why this is such a problem, we need to think about what information means in physics. In physics, information is the fundamental property of every particle in the universe. It tells you everything you could possibly know about that particle. And one of the most basic rules of our universe is that this information can never ever be truly destroyed. It can be scrambled, like shredding a document, but in principle you could always piece it back together. This rule, the conservation of information, is a cornerstone of modern science. It is fundamental to quantum mechanics, the theory that describes the strange world of atoms and particles. Herein lies the paradox. We have two great pillars of modern physics. The first is Albert Einstein's theory of general relativity. The second pillar is quantum mechanics. For most of the universe, these two theories work perfectly in their own domains, but at the edge of a black hole they meet and they clash. To truly understand what a black hole is, we must first look at the stars. Stars are giant nuclear furnaces. They spend their lives fusing lighter elements into heavier ones in their scorching cores. This outward push of energy perfectly balances the inward pull of the star's own immense gravity. For millions or even billions of years, a star exists in this delicate equilibrium. But like all things, stars have a finite lifespan. They eventually run out of fuel. When this happens, the balance is broken, and gravity, the ultimate cosmic force, takes over with dramatic consequences. The star's core collapses catastrophically under its own weight. This collapse happens in less than a second, triggering a stupendous explosion known as a supernova. If the original star was massive enough, the core continues to collapse. The pull of gravity is so overwhelming that nothing can stop it. It crushes protons, neutrons, and electrons out of existence. The material is squeezed into a space of zero volume and infinite density. This is the moment a black hole is born. It is the ultimate gravitational victor, a monster created from the ashes of a dead giant star. Black holes are surprisingly simple objects. While the process of their birth is chaotic and complex, the final result can be described by just three properties: mass, spin, and electric charge. That's it. All the other intricate details of the star that formed it are lost. The black hole that remains is defined only by these three numbers. The most famous feature of a black hole is its event horizon. This isn't a physical surface you could touch. Instead, it is a boundary in space-time. It is the point of no return. Imagine you are in a boat on a river that flows towards a giant waterfall. Eventually, you cross a point where the water is flowing faster than you can possibly row. You are now destined to go over the falls. For you, the experience would be very different. You would feel nothing special as you cross the event horizon, sailing past the point of no return in a finite amount of time. At the very heart of the black hole, general relativity predicts a singularity. This is a point of infinite density, where all the matter of the original star is crushed into oblivion. When physicists talk about information, they mean something very specific and fundamental. Think about a simple object, like a billiard ball on a table. Its information would include its exact position, its speed and direction, its mass, and its spin. It is the universe's ultimate blueprint for reality, written in the language of mathematics and physical laws. This concept is absolutely central to how we understand the cosmos. The universe, at its core, appears to follow a set of unbreakable rules. We call these the laws of physics. Imagine the universe is a grand cosmic film. Every particle is a character, and its information is its script, a complete log of its every action and state. The idea that a part of this script could simply vanish into thin air is unthinkable. It would mean the story has a hole in it, a moment that is disconnected from everything that came before and after. The notion that a black hole could be a place where this fundamental rule is broken is therefore deeply disturbing. One of the most important rules in physics is that information can change its form, but it can never be truly erased from existence. Think about burning a piece of paper that has a message written on it. When you crack an egg into a bowl and whisk it, you are destroying its original structure. The information about their original positions has been thoroughly scrambled. However, in principle, it has not been destroyed. This principle of conservation of information is a key feature of quantum mechanics, our theory of the subatomic world. One of the core tenets of quantum theory is that the wave function evolves smoothly and predictably over time. So, when an object falls into a black hole, quantum mechanics insists that its information cannot be destroyed. Let's say you throw a book, full of stories and knowledge, into a black hole. General relativity seems to tell us that the book is crushed at the singularity and its information is wiped from the universe. But quantum mechanics says no. That information must be preserved. This is the heart of the problem. We have two great theories giving us two completely different answers. And for physics to move forward, this contradiction must be resolved. For a long time, physicists thought of black holes as perfect cosmic prisons. Once something crossed the event horizon, it was locked away forever. This simple picture was completely overturned in 1974 by the brilliant British physicist Stephen Hawking. He was trying to understand how the strange rules of quantum mechanics would apply near the edge of a black hole. Quantum mechanics tells us that even empty space is not truly empty. It is a bubbling, frothing sea of virtual particles. He wondered what would happen if a pair of these virtual particles appeared right at the edge of a black hole's event horizon. He realized that it was possible for one particle of the pair to fall into the black hole while the other one escaped into space. This steady trickle of escaping particles would appear as a faint glow, a form of radiation coming from the black hole. This astonishing discovery became known as Hawking radiation. Over unimaginable timescales, far longer than the current age of the universe, a black hole will radiate away all of its mass until it evaporates completely, disappearing in a final puff of energy. Stephen Hawking's discovery was a triumph of theoretical physics. It beautifully connected the three great theories of science: general relativity, quantum mechanics, and thermodynamics. But this brilliant insight came with a very deep and troubling problem. Hawking's calculations suggested something truly shocking about the nature of this radiation. He found that the particles escaping from the black hole were completely random. Imagine you build a fire and use it to burn two different objects, a detailed encyclopedia and a simple block of wood of the same mass. However, Hawking's calculations suggested that if you threw the encyclopedia and the block of wood into two identical black holes, the Hawking radiation that eventually came out would be exactly the same in both cases. This created a terrifying prospect for physics. The information that described the encyclopedia, every word, every sentence, every diagram, seems to have been utterly and permanently erased from the universe. Hawking himself was initially convinced by his own calculations. He famously argued that the loss of information in black holes was real. He believed this meant that our understanding of quantum mechanics was incomplete. The puzzle that emerged from Hawking's work is what we now call the black hole information paradox. Honestly, it is one of the deepest and most profound problems in all of science. The paradox arises from a direct conflict between two of our most successful theories. They cannot both be right, at least not in their current forms. This is not just an academic debate for physicists. It points to a deep gap in our knowledge of the universe. It tells us that our current theories are incomplete. The information paradox is like a giant signpost, pointing directly at this missing piece of the puzzle. Solving the paradox would likely mean finding this new theory and revolutionizing our understanding of space, time, and the very nature of reality itself. The information paradox plunged theoretical physics into a state of crisis that has lasted for nearly 50 years. It is not a small problem that can be easily fixed with a minor adjustment to our equations. It challenges the very foundations of what we believe about the universe. The principle of information conservation, or unitarity, is not just a preference. It is deeply embedded in the mathematical structure of quantum theory. If information can be destroyed, it implies that energy might also not be conserved, which would unravel much of modern physics. The problem is so severe because it suggests that the universe could be fundamentally unpredictable. This crisis has forced physicists to question their most cherished assumptions. Could general relativity be wrong about what happens at the event horizon? Or is quantum mechanics the theory that needs to be modified? Ultimately, the information paradox is a powerful engine for progress. It forces scientists to think in new and creative ways. It pushes them to explore radical ideas and to search for a new theory that can resolve the conflict. It is a puzzle of the highest order, and its solution is expected to reveal something incredibly profound about the universe. The crisis is not a sign of failure, but a signal that we are on the verge of a major breakthrough in our quest to understand the cosmos. One of the most radical and mind-bending ideas to emerge from the information paradox is the holographic principle. This principle suggests that our common-sense picture of the universe might be, well, completely wrong. It proposes that the information to describe a volume of space can actually be thought of as being encoded on a two-dimensional surface that surrounds it, kind of like how a three-dimensional hologram is projected from a two-dimensional film. Now, this might sound like pure science fiction, but it's actually a serious idea rooted in the mathematics of black holes. A black hole, for example, is the most information-dense object possible, and its information content is perfectly described by the area of its event horizon. According to this idea, the universe as we experience it, with its three dimensions of space, might really be a holographic projection of information stored on a distant, flat boundary surface. So how does this help with the information paradox? Well, the holographic principle changes the question entirely. If all the information about what falls into a black hole is stored on its event horizon surface, then it was never truly inside in the way we usually think. From this perspective, it's much easier to imagine how the information could be encoded in the outgoing radiation. The paradox seems to, well, just dissolve. This viewpoint offers a beautiful resolution. The idea of black hole complementarity seemed like an elegant solution. However, in 2012, a group of physicists identified a major flaw in this picture. They argued that if the information is held at the event horizon, it would lead to a bizarre and honestly violent consequence. Instead, it would be a seething, high-energy wall of fire that would instantly incinerate anything attempting to cross it. This firewall paradox arises from a deep conflict in quantum mechanics. A fundamental quantum rule states that two particles that are entangled share a single, unified existence. What happens to one instantly affects the other, no matter how far apart they are. The problem is, quantum mechanics forbids a single particle from being fully entangled with two different systems at the same time. It's a rule known as monogamy of entanglement. So, we are left with a trilemma. We must choose which sacred principle to abandon. Is quantum mechanics' rule of entanglement wrong? Is information truly lost after all? Or is Einstein's idea of a smooth, unremarkable event horizon incorrect? The firewall paradox sharpens the information problem to a razor's edge. The debate continues to rage with honestly no clear consensus in sight. In recent years, a new and promising avenue of research has opened up. It suggests that the solution to the paradox might not require radical new principles like firewalls or holography. Instead, the answer might lie in tiny, previously overlooked details in our calculations. The original problem arose because Hawking's calculation of the radiation was an approximation, but we know that at the smallest scales, space-time itself must have a quantum nature. This line of thinking focuses on something called quantum extremal surfaces. The core idea is that quantum gravity effects create a special surface inside the black hole. These connections are sometimes visualized as wormholes in space-time, linking the interior of the black hole directly to the radiation far away. Through these quantum wormholes, the information inside the black hole becomes encoded in the radiation outside. This process happens slowly over the black hole's lifetime. Crucially, this approach seems to solve the paradox without creating a firewall and without violating the laws of relativity at the event horizon. In 2019, calculations showed that the information content of the radiation does indeed follow the path we would expect if information were conserved. While the precise mechanism is still not fully understood, it feels like physicists are finally closing in on a solution. The paradox that has puzzled the greatest minds for 50 years may be yielding to a deeper understanding of the quantum nature of space-time itself. The journey into the heart of a black hole is a journey to the very edge of our understanding. For nearly half a century, the information paradox has stood as one of the greatest challenges in all of science. It represents a profound clash between the two pillars of modern physics: Einstein's general relativity, which describes the grand sweep of the cosmos, and quantum mechanics, which governs the strange dance of particles. Today, the tide has turned. The consensus growing among physicists is that information is never truly lost. Recent breakthroughs, involving ideas as strange as quantum wormholes and holographic surfaces, have provided a mathematical framework showing how information can escape the clutches of an evaporating black hole. It seems the information is not destroyed, but is intricately scrambled and encoded in the faint Hawking radiation that leaks out over eons. The paradox that once seemed insurmountable is beginning to yield, not by breaking our theories, but by weaving them together in a more profound and unexpected way. Fully resolving the paradox requires a complete theory of quantum gravity, a mathematical language that can speak of both stars and atoms with equal fluency. This is the holy grail of modern physics. Finding it would not only solve the puzzle of black holes, but would also allow us to understand the very first moments of the Big Bang and the ultimate fate of the cosmos. The information paradox has been our guide, a beacon showing us where our knowledge ends and where the next great revolution in science must begin. The quest to understand what happens inside a black hole is a testament to our innate curiosity, our desire to read the universe's rulebook, and our unyielding belief that, in the end, the universe is a rational and knowable place. The adventure continues.